All right. So, chapter 14 is a long chapter. And we're going to continue talking about acids and bases by giving a few more definitions of what an acid is and what a base is. Okay? So, earlier we defined an acid as a proton donor. Okay? And a base is a proton acceptor. There wasn't even, we didn't talk about this definition, but an earlier definition of an acid was a substance that produces H plus in water, okay? And for the Arrhenius base definition would be something that produces hydroxide in solution, which wasn't very consistent with ammonia, because ammonia, NH3, didn't have a hydroxide, so that was a bad definition. Then we came up with the Bronsted acid, proton donor, proton acceptor. That one worked really well. Okay. Now a Lewis acid is a little different because now it's talking about pairs of electrons being transferred. Okay. So a Lewis acid is a substance that can accept a pair of electrons, whereas a Lewis base is a substance that can donate a pair of electrons. And you'll talk about Lewis acids and bases a lot in organic chemistry. That'll be kind of a more of a big deal in organic chemistry. But here we can see that with these substances, okay, the Lewis acid is a substance that accepts the electrons. So here the H plus is accepting the electrons, so we define it as the acid, whereas the OH minus is donating the electrons, so we define it as the base as far as the Lewis acid base goes. Okay, here's another example, H plus and NH3. NH3 donates the electrons, or you could even say these electrons attack this hydrogen. And so they're donating their electrons to hydrogen to share them in a covalent bond, and you get NH4 positive. Okay? So this is just kind of another way, and in organic chemistry it'll be a really good way to perceive the chemistries that are occurring. And in organic chemistry, that's what it's going to be. You're going to be a lot less math. I don't even think there's hardly any math. It's more understanding reaction mechanisms and learning the reactions and how these certain things react together, and that's going to be part of it. Those electrons attacking, the Lewis base is attacking the Lewis acid, the electron deficient thing with the electron, what's the word? The thing that has more electrons, okay? All right, so here we go. Boron has the electron deficiency, ammonia is going to attack it, and you get the combination of those two things. Okay, that's kind of organic chemistry right there, a lot of it. This is your acid, this is your base. No protons are donated or accepted, right? So no hydrogens were shifted around here. So that's why we have to come up with another definition for these types of reactions as to what is the acid, what is the base in this. Okay. Yes. I don't think we need to spend a lot of time on that. Let's go ahead. Okay. Now I want to consider this definition of the common ion effect. So, in the Chatelet's principles, we learned that if you increase the concentration of something, that shifts your equilibrium, right? It shifts your equilibrium. Well, that's what we mean by the common ion. So, in an acid-base situation, you have hydroxide ions and you have H plus ions. Well, if I add more H plus, then I'm saying that I'm adding more of that common H plus ion. Okay? Or the OH minus. If I add more OH minus, I'm increasing the concentration of OH minus. That is the common ion effect. Okay? It shifts the equilibrium caused by the action of a compound having an ion in common with the dissolved substance. Okay? So if you dissolve something into the solution, like sodium hydroxide, then you're increasing the hydroxide ion concentration. That's the common ion that you're increasing. Okay? Okay, so consider the mixture of sodium acetate and acetic acid. Okay, so here we see sodium acetate dissociates into sodium and acetate. Okay, 100% dissociation there. And this is acetic acid. So if I have acetic acid and I dissolve sodium acetate into acetic acid, well, I already had some acetate. Okay, but let's just say this is a 0.1 molar acetic acid solution. What is the concentration of this ion? These are at 0, these are at 0. No, we have to figure this one out. The Ka for this equals 1.8 times 10 to the negative 5. So essentially, this is equal to x squared over 0.1. What is it? So 1.8 times 10 to the negative 5 times 0.1. Let's take the square root. What is x? X is what? Okay, 0.0013 molar. So I have 0.0013 molar acetate. That's not a whole lot, right? So I have 0.1 molar of this, and I only get 0.0013 molar of the acetate. That's a very small amount, right? So what happens if I dissolve sodium acetate into this acetic acid? I increase the concentration of this. So if it was 0.1 molar of this, then I would add 0.1 molar of this, and I would essentially have 0.1 molar of both things now. Okay? And they would be in equilibrium with one another. So now I've created a situation where I have close to equal concentrations of the acid and the base on both sides of the reaction. Okay? That's a special type of solution. When I do that, when I have an equilibrium equation and I create equal amounts of the common ion on both sides of the reaction, okay, then we give that the name of a buffer. Okay? All right, so here we have, this is a base. It's a base. And here's its weak acid. Okay, we have a Ka for it. Now, the Ka for this acid, right, is H plus times A minus over HA. Now, if I solve for H plus, it equals the K times that divided by A minus. Okay. So we can easily see that this term if we take the negative log of H plus, that gives us what? pH. The pH. So if we set everything to the negative log of it, let's say the negative log of H plus, the negative log of the Ka gives me a what? pKa, right? So the pH equals the pKa plus the log of the base over the acid. Well, here it is. Plus the log of the base over the acid. Okay? And this becomes an equation where I can easily solve for the pH of a solution of common ions, or meaning of a buffer solution that has significant amounts of base and acid, and I can solve for the pH of it. This is the Henderson-Hasselbalch equation. Okay? And we often are trying to solve for the pH, right? That's what we want to do. So it's set up to do that. You don't have to use this equation to solve for the pH. You could just set up a Rice table and solve for X. But that's exactly what this is doing. Okay? It's just doing that. But you don't necessarily have to use this equation if you just want to use the Rice table. If you're more comfortable with that, fine. But this equation will be given to you on your reference material, and it would be set up in this way. pH equals the pKa plus the log of the base over the acid. Okay? So as long as you know what the base concentration is and the acid concentration, you'll know the molarities to put there. And this equation becomes very easy to use. Okay? So what is the pH of a solution containing 0.3 molar formic acid and 0.52 molar potassium formate? Okay? Well, pH equals the pKa plus the log of the base over the acid. Okay? So I want to solve for the pH. I need a pKa, right? Let's see, did they give it to us on here? What's going on? It's on the bottom. Okay, they don't give us a. Okay. Okay, well that's not what I wanted. Okay, so can somebody take the anti-log of this? Negative anti-log of 3.77. What's the K? Because you'll often be given the Ka, not the pK. They're not going to give you the pK. So what is the Ka here? Okay. 1.7 times 10 to the negative 4. All right. That's weird. Okay. So the pH equals the pKa plus the log of the base over the acid. So you'll often be given a Ka like this, and it's already done it for you. But though you'll need to convert it from Ka to pKa. And that'll be 3.77 by taking the negative log of the pKa plus the log of the base concentration. Which one's the base? The one with less hydrogens is the base. The one with more hydrogens is the hydrogen donor, the acid. Okay, so what number goes on top? 0.52 divided by 0.30.
Why was that on top again?
I'm sorry?
Why is it the base?
Why is it the base?
Yeah.
Because it has less hydrogens. Okay, so the thing that has less hydrogens is the base. The thing with more hydrogens is the acid. That's how you can identify what is what. Which one's the base, which one's the acid. Okay? So 0.52 divided by 0.3, what is that? Okay, now take the log of that. What do you get? .328? 238? Okay, say, what was your question?
I'm sorry, so how did you get the pKa, 3.77?
Okay, if you take the negative log of 1.7 times 10 negative 4, which is your Ka, it'll give you the pKa. Just like for the pH, you take the negative log of the H plus will give you the pH.
And when we use this formula, is this just another way to find out like the pH? Or like when we use this formula?
When you have a buffer.
And how do we know we have a buffer again?
Because you have significant amounts of both acid and base.
So originally they were just supposed to get it.
Originally they gave, yeah, I mean, yeah, we could always look it up, but they should have given us, in the question they would give you the Ka. You need that. You have to have that to find the pKa, right? So that would be information you would have, okay? So the pH here, so look what's happening. pH equals 3.77 plus 0.238. 4? 4.008. Wow, I can't hear you guys at all. 4.
Like when you add them together.
Oh, when you add them together.
Yeah, that's the pH.
0.238. Is that what it was? Okay, good. That's good. We'll get there. Okay, equals. Okay, go ahead. Tell me what 4.
0.008.
All right. So what happened to the acidity? Did the pH go up or down? The pH went up. The acidity went down. Okay, the pH went up because this has more what? Base than acid. Okay, let's flip those numbers. What if it was 0.3 over 0.52?
So the pH would go down, the acidity would go up.
Oops. Okay? This is a check. This is a way to check yourself that you're doing this right. Okay? So if I have more acid than base, then the acidity should go down. Okay? So at 3.53, from 4.008 going up, or 3.53 going down. It's the same ratio. Okay? It's just inverse. Okay? All right, so now what I want you to see is if I had a 0.3 molar, well, that's not really showing it here. But what we're going to see later is that if I change the acid concentration of this, so let's say I add some hydrochloric acid to this thing. That's going to change the concentration of H plus in the buffer system. And everything is going to have to re-equilibrate. Okay? And it's going to have to re-equilibrate so that it will equal that 1.7 times 10 negative 4 again. All right? But, so if I increase the acid concentration, it's going to react with the base. And the base, well, let's just use this example. The base concentration would decrease. Let's say it went down by 0.01. And this increased by 0.01. Okay? Because if this decreases by 0.01, this decreases by 0.01, this will increase by 0.01. Okay? So if that's the case, what's my new ratio here? 0.51 and 0.29. Oh, add, that's right. Subtracting, so thank you. Go away. Doesn't want to go away. There we go. 3, 1. Okay? All right. So what is it when I do that? 0.216 here. Okay? And that doesn't change the pH very much, right? 3.98. So it was 4.008, now it's 3.98. That's not a significant change. Okay? This is why we call this a buffer system, because it maintains the pH. So our blood maintains our pH at 7.4 even though I go and eat a bag of sour candy. My blood pH doesn't spike. It doesn't change that much because I have a buffering system in my blood. And this is what it's doing. It's buffering this through the Chatelet's principles, because if I increase the H+, it shifts, it tries to bring that H+ down by shifting it towards the other way. So I increase H+, it brings it down and shifts it the other way. And it buffers out the changes. So as long as I have enough of this to buffer how much acid I added. So if I had added 0.1 moles of acid to pure water, then the pH would be 2. So adding straight acid to water changes the pH very quickly. But here I can see I buffer those changes. I buffer those changes, and it doesn't get changed very quickly. The 0.1 molar H+ that I added just gets buffered out because I have enough of this. Now if I had added 0.6 molar H+, that would have overcome the base, that would have overcome the buffering system, and I would not have been able to buffer this. Okay? Then my pH would have gone from 0.52, and it would have got buffered out, and I would be left with like 0.1 or so acid left, and then that would be the pH of my system because it overcame the buffer. The buffer got rid of most of the added acid. Okay, it got rid of 0.52 molar of the added acid, but since it was 0.6, I have 0.1 left over. Okay, and so now my resultant pH is based on that leftover acid. Okay, and we'll look at all that. But that's what we're going to be doing and trying to understand with these buffer systems. We're going to try to understand if I add this much acid or base to a buffer system, it's going to have to re-equilibrate. And when it does, I end up with new concentrations like this. I end up with new concentrations, and then I will end up with a new ratio, and I will end up with a new pH. And if that pH, if the buffer system was able to completely buffer out the changes, then the pH will not change very much. But if I overcome the buffer, then it will change drastically, okay, by that point. Okay, so they're going to show you through the Rice table first how this is done. Okay. So this should all look familiar. Like I said, you could do this through a Rice table. Okay, 0.3 minus x, 0.52 plus x. Okay, and then your Ka equals the x times 0.52 plus x on top over 0.3 minus x on the bottom. But if you just consider, this is what the Henderson-Hasselbalch is doing. It's just dropping negative x and plus x. Okay? It's considering those to be insignificant. And then you get this. And if you rearrange it so that x is out here, so x equals your Ka times your base, which is, well, in this case, the way I'm setting up would be the acid, 0.3 over 0.52, okay? And that would equal your x, and I could solve for the H plus, okay? But if I take the negative log of everything, then I have the pH equal to the pKa, and it would be minus the acid over the base. But if I say plus the log, then it's the base over the acid, and I invert that.
Can you explain what you did over there, the common odd effect?
Okay, so the reason that we're dropping x here is for the same reasons we would do it with all the other acid equations we're using, where we're just considering x to be insignificant. The change in this would be insignificant, so I can just assume that it rounds back to 0.3 and 0.52. Yes?
So then the x's aren't canceling themselves. Like they're not canceling themselves out.
No. They don't cancel themselves out because it's not multiplication. It's addition and subtraction, so you can't cancel it through division. But it will, if we consider it to be insignificant, we can just drop it. Okay?
You were showing with the buffers and how even with the buffer there was not a significant change at all. Is that why they dropped the x? Because it's just not going to make a difference, really?
Exactly. Because if I subtract 1 times 10 to the negative 4 from 0.3,
This still would be 0.3.
it rounds back up to 0.3. It's going to be like 0.299999, right? So it's just like not even significant how much it changes it. So we just round it back to 0.3. Okay?
So they split it up. You split up the HCl
Split up what?
for that reaction. Like when we did it, we just took
That's only for.
the base, put it over to the, right, we used that pH equal pKa was log. They took it, why'd they use the COOH?
Why did they use HCOO minus as the base? Is that what you're asking? This?
Yeah, well, in that, so we don't need to do that step. We can just put the HCOOK over the HCOOH basically, right? With the other formula?
Are you asking like we don't have to do the rise table for this at all?
Yeah.
Yeah.
Oh, okay. You don't have to do a rice table if you have a question like that. 0.3 molar formic acid and 0.52 molar potassium formate, okay? Because you'll know what the base is, you know what the acid is, and you can use Henderson-Hasselbalch. So no rice table needed because you know the concentrations, and this equation is making the assumptions already to drop negative x and plus x here.
Right.
Okay? And it's just incorporated into the equation right here. Okay? But when we make changes to a buffer system, then we want to use a rice table. Okay? Then we'll set up a rice table to calculate the changes that occur, and then we will use Henderson-Hasselbalch again after we determine the new concentrations of everything. Okay? But yes, that question right there, all you would need is Henderson-Hasselbalch and the concentrations of both the acid and the base in the buffering system, and you could calculate the pH. Okay? Very simply. Okay.
And HCO minus just came from the HCO. Well, because potassium is just
The base
It's just there.
concentrations of the base.
The what came from what? Say it again. The H plus?
No, I know where that came from.
This.
We're using that as the base up there because the potassium's just kind of there.
The potassium's a spectator ion.
So we just assume.
It's a delivery ion. It delivers the acetate,
Right.
or the formate.
So we're just assuming that that's the base,
It just has the net.
or that's the same ACO minus.
Yeah, we could even just put this back here if we wanted.
Right. Okay.
Okay, but yeah, it's just showing the potassium isn't actually part of anything. It's just allowing you to dissolve the acetate into the solution. That's all it's doing. Okay, it's a salt when it has potassium, and then when you put it into solution, the K plus and the HCO minus come apart. Yes?
So it's just a spectator ion, it's not considered like a catalyst? 'Cause I know
That's
that-
right, it's just a spectator ion.
Okay.
That's all it is, just a spectator. Okay? A spectator ion is something that has no bearing on the reaction at all.
When
It
you're
just,
looking at something like that, how do you know which ones are the spectator ions? Just-
It's the metals.
well, if you look at the acid, HCOOH, the only difference between it and the base is one hydrogen is replaced for that potassium, right? So you could make the assumption that this, if you write your reaction like this, you could even write it out before you even look at that, and see that that potassium is just a spectator in this. It's a delivery molecule for the HCOO minus, okay? Because here, I know I have to donate a hydrogen in equilibrium and create that, okay? So, okay. All right, so our pH came out like we found. pH is 4.1, 4.01. Okay. So very important in a buffering system, you must have both the acid and the base. Okay? You have to have both the acid and the base in order to be considered a buffering system. Now, if you just have the acid, it will buffer changes that are only changes to the hydroxide concentration, because the acid will react with hydroxide. Okay, so as long as you're not adding acid, so if I have just the acid and I add more acid, it can't buffer anything because there's no base, there's not enough base present to buffer changes of adding acid. But if I have both the acid and the base, it will resist changes to both things. Okay? Okay, so here's acetic acid and sodium acetate. Okay, so if I have a buffer of acetic acid and sodium acetate, here's acetic acid, here's sodium acetate. Do you recognize which one's the acid, which one's the base? Okay, this one's the acid, this one is the base. This is a spectator ion, sodium. It's a spectator ion because it's going to produce this acetate. So, if I add acid to a buffering system of acetic acid and sodium acetate, what does the acid react with? It reacts with the base. Okay? The acid will react with the sodium acetate, which is the base, right? We just labeled it. This is the base. So if I add acid, it will react with the base. And whatever the concentration of the acid that I add is going to be subtracted from the base concentration. Okay? And it will be added to this. Because if we set up a rice table, we would easily see, let me go backwards here a little bit. Okay? If I set, whoa. That was a big jump. All the way to the beginning, huh? Okay, so if I set this up in a rice table format, so let's say I have 0.3 molar acetate and I have 0.3 molar acetic acid. Okay, and I add 0.02 molar H plus. then it's going to be minus x, minus x, and plus x. Well, I know what x is, okay? X is 0.02 molar. This goes to 0 minus 0.02 molar. Okay, I subtract from there, and I add 0.02 molar here. Okay, so I increase that concentration. Okay, now I have two new concentrations. The H plus has been depleted because it reacted with this, and it depleted this, some of this down to, it depleted 0.2 molar of this down to 0.28 molar, and it increases the because of equilibrium, it increases the concentration of this. That reacts with the H plus and shifts it this way, and it will go to 0.32 molar. Now I can recalculate my pH by simply putting the base over the acid, 0.28 over 0.32. pH equals the pKa plus the log of 0.28 over 0.32. And that'll be how I calculate my pH. So after I find the adjustments, I find the new molarities of the acid and the base in the solution after addition of an acid or a base, I can then recalculate. The acidity is going to be, it slightly increases the acidity because the acid is now higher than the base. Mm-hmm. Yes?
This is kind of going back to a little bit, but you were talking, or you were saying to us about how we can tell if which one's the acid, which one's the base by the amount of hydrogens. But when we were talking about the Lewis acid, we were talking about like boron trifluoride or something, and then that was the acid over the one that had more hydrogens.
Yeah, that's a different situation. And with the Lewis, we're not going to be using Lewis acids to do these kind of stuff.
So we don't
okay?
have to worry about that.
I won't make you do a buffer system of a Lewis acid.
Okay.
It's not going to. There aren't any really necessarily, but this is this will be more just kind of Bronsted acid-base definitions that we're going to deal with for these kinds of things. Okay. So yeah, you won't have to worry about Lewis acids or bases very much. That's more of just an introduction to it, and for when you get to organic chemistry, you'll be using those more often. Okay. But here we're going to be focusing mostly on the Bronsted definition of an acid and a base. Okay. Okay, let's go back to that one. So if I add an acid, it reacts with the base. If I add base, like sodium hydroxide, let's say I added sodium hydroxide, it would react with the acid of the buffer, and it would reduce the concentration of the acid. Okay, so it would, if this was 0.3 molar and this was 0.3 molar, like our earlier example, 0.02 molar minus 0.02 molar, that goes to 0. This one minus 0.02 molar, that goes to 0.28, and this one will go to 0.32 plus 0.202 molar. Okay, and it will decrease the concentration of the acid and increase the concentration of the base by the amount that you added. Okay, so that's where these Rice tables can kind of help us with the acid, with the buffering systems, because they help us see the changes, and then we can recalculate the pH after we've made the changes through the common ion. Okay? All right. So this is just showing that HCl added. I'm adding hydrochloric acid to this buffer. It's an acetic acid buffer. Okay? So HCl is going to react with the acetate, and as it does that, it's going to create more acetic acid. So the acid concentration is going to go up, the base concentration is going to go down, okay? And you can see here that the pH is being maintained, whereas if I was just in straight water, the pH would drop very quickly. It would not be maintained, okay, because there's nothing to buffer it.
It would be the case because hydrochloric acid is the acid, and the acetate is the base, right? But it has more energy.
What you're looking at is this. This is the acid, and this is the base. HCl is an acid, but we added HCl, and they're just saying it's reacting with the base and producing more of the acetic acid. So as it reacts, it produces more acetic acid, and then we can recalculate those concentrations. So I don't know if that's what you're...
No, yeah.
Okay. This is having a time today. Okay, which of the following are buffers? Is KF, HF a buffer? Can you make a buffer out of KF and HF? Okay, the way you know is if it establishes an equilibrium, meaning it has to be a weak acid or a weak base. So, does KF and HF, is HF a weak acid? Yes. So yes, you can create a buffer from that. KBr, HBr, is HBr a weak acid? It's a strong acid. No, you cannot create a buffer. Sodium carbonate and sodium bicarbonate. Yes, that's a weak acid and its conjugate base. So we could create a buffering system there for that. Okay. Okay. Calculate the pH of the 0.3 molar ammonia, 0.36 molar ammonium buffer system. Okay, so we want to first calculate the pH of the buffer system. The KB for this is equal to 1.8 times 10 to the negative 5. It's a constant. It would come from a chart or a table or the question. So the pH equals the pKa plus the log of the base over the acid. Okay, so go ahead, tell me what the pH is here. Do you guys get a pH? What is it?
9.18.
Okay.
It's a base, so it seems to work out.
Okay, so 9.18. Are you guys getting that too? Anybody else?
After the addition. Oh, I didn't even.
No, we're not doing that yet.
Oh, okay.
We're doing this first part. What is the pH of that buffer system? Calculate the pH of this buffer system. We'll do the second part next. Okay. Okay, so this is what it should look like. Okay. Now I gave you a KB, but this time you converted. You did convert it to the KA. You noticed that right away, so good job. Last time you guys were a little more confused about that, so did good on that. You found the pKa to be about 9.25. 9.25 plus a log of 0.3 over 0.36, you get 9.17 or 9.18. Okay, good. Now, what is the pH after the addition of 20 milliliters of 0.05 molar sodium hydroxide to 80 milliliters of the buffer solution? So when I add 20 milliliters to 80 milliliters, that changes what? Volume. When I change the volume of something, that dilutes it. That dilutes what was ever in there or whatever I added. Okay? So that means my concentrations have changed based solely on volume. Okay? So if I change the volume, it's going to change the concentration, so I have to reconsider all of that. How am I going to do that? What is the initial concentration of NH4? Okay, it was 0.36, but now that I added 20 milliliters, it went from 80 to 100. How do I find dilutions? This is a big confusion for you guys in the lab yesterday. Yeah, okay. Dilutions are calculated by M1 V1 equals M2 V2. We want to calculate M2. M2 equals M1 V1 over V2. Okay? That's how I do it. I do that. I'm going to calculate that concentration change here for all of these.
And why do you want M2?
Versus M1.
Just why did you choose that?
Because that's the new molarity after the dilution. I started out with 0.36 molar of NH4, and I'm going to dilute it when I add 20 milliliters of this sodium hydroxide. So I have to calculate what the new molarity is after the addition of the 20 milliliters.
Then you're going to find the pH after that?
Yes. Well, we're going to, yes. That's only one step of this. This part is to find these initial concentrations after the addition of the OH minus, sodium hydroxide. Okay? So, what is the new concentration of NH4 plus?
0.288.
Okay? So my M1 is 0.36. My V1, my initial volume was 80 milliliters. Okay, do you see where I get that right there? We were using 80 milliliters of this buffer system. What is my V2? 100. The final volume after the addition is 100 milliliters, right? Because I took 20 and I added it to 80. So 0.36 times 80 divided by 100, what was it?
0.288.
So the new concentration of NH4 then is 0.288 molar. Okay? That's my M2 for
So we just have to know to add, like when you say adding NaOH, we just gotta put some base on it on that side, on the left side.
you're reacting the base with the acid, right? The acid is reacting with the base. If it was, if I was adding acid, I would write this the other way, because it would be the base reacting with the acid. Does that make sense? Okay? It would be the other way. I'd write it the other way because I'm reacting a base here.
So
I'm
if you
adding
had
a base.
HCl, we would add H plus over on the right side.
If I was adding HCl, I would write it like this: NH3 plus HCl, or I'd just say H plus actually. Plus H plus produces NH4 positive.
Because the C on the spin.
Yes. It's just a delivery ion. Okay? Because it's the base reacting with the acid. Here it's the acid of the buffer system reacting with the added base.
That's why the NA is not there. Because the spectator is not.
That's right. Sodium hydroxide. This is the sodium hydroxide, okay, that I added. So, I know what the initial concentration of the NH4 is, okay, but what is the initial concentration of the OH minus?
0.5.
No.
No,
Did I dilute that as well?
you sure did.
I did.
You son of a
It's
gun.
in 100 milliliters now. It was 20, now it's in 100. Okay? So, once again, M2 equals M1 V1 over V2. Okay? So what is the OH minus?
0.01.
Okay, water, we don't have to worry about the concentration of water. All right? What is the concentration of NH3? Do the same thing. What is it? 0.24 molar. Okay? All right. So do we see what happened? These molarities changed. We have to change the molarities of everything due to dilution. Now I know the concentration of everything in the solution initially. The initial concentrations of everything. Now this hydroxide is going to react with this until one of them reaches 0. Which one reaches 0 first? This hydroxide, right? So minus 0.01 molar minus 0.01 molar. This one goes to 0. What is the new concentration of NH4 plus? 0.278. Okay? And this is going to be plus 0.01 molar. 0.25 molar. Okay? Now what do I do? How do I find the pH at this point?
We do that. We use the same formula.
That's right. Right here. I already have half of it. I just need to change these. The base over the acid. Which number goes on top?
NH3.
0.25. What number goes on the bottom? 0.278.
So the ones that we subtract is either the base or the acid, like the OH minus or the H plus
The one that you subtract
or
If it was like, if acid was being added, then you would subtract H plus, right, on the both sides.
if I was adding acid, I would rewrite this equation so that NH3 is over here instead of NH4, and then I would subtract the acid from both the NH3 and the acid, and I would increase the concentration of the NH4. Okay, I would write that equation the other way, and I would show that it's adding the acid.
Our pK doesn't change with the new molarities?
The pK, no, it's a constant. It'll remain constant.
Okay.
So your Ka doesn't change. It will stay constant. The only thing that changes are the concentrations of the acid based on how much hydroxide you added, and the concentration of the base based on how much hydroxide you added. Okay. All right. So what's the new pH here?
9.21.
Okay. So it went from 9.17 to 9.21. Not a gigantic change, but we added a lot of hydroxide. Okay, but it didn't cause the system to change its pH very much. Right. That was
We
it.
don't really do a proper rice table for that, right? Because that would be.
No, not. I guess not a. You don't really do an equilibrium. You don't show equilibrium. We're not showing equilibrium here because that minus x and plus x of the equilibrium is insignificant. So we just take the initial concentrations after the reaction, and we use those as our concentrations for the Henderson-Hasselbalch equation. Okay. All right.
We're supposed to stop you, right? We'll need a break.
Let's stop. Yeah, go ahead. We'll take 10 minutes.
In a buffer system, you can add a strong acid to a weak acid buffer system, right? You can't use that for strong acid because strong acid is not buffer. So like the hydrochloric acid is the strong one, but you can add it to change the acidity.
Yes. So I add HCl to act on the buffer, but HCl itself cannot be a buffer. Does anybody else need a review sheet?